checking 1, 2, 3. Right. We begin. Right. Before we start, what we learned from last time is iteration by parts. So we just want to write out the formula again. Integral of u times dv is equal to uv minus integral of v times du. Right. And last time what we did was going straight forward from that formula. Now before we go back to that, in this case we use a little bit different method, but we have to review a little bit. Right. So we go over integral and derivative again, but this time we have the constant k. Right. Well, let k be a constant. So derivative of sine of k times x, derivative of sine is cosine. But when we multiply the variable or the angle x by k, derivative is using the chain rule derivative of that, and so we have the k here. Right. Cosine derivative of cosine is negative sine, and this time we multiply constant k to it. cotangent is secant square, and then we multiply constant k to it. Cotangent is negative cosecant square and multiply by a constant k to it. Secant is secant x tangent x. This time we have kx, and then multiply that constant k in front. Cosecant is negative cosecant cotangent kx, and I think we have e to the kx. Yes, so e to the kx is k e to the kx, and the last one ln of kx. And this one is a little special. So up to this point, I will say that again. By the way, what we really mean when we take derivative of all of this, then derivative of sine is cosine of a parentheses, and then the derivative of the parentheses square, and the derivative of kx is k. Derivative of kx is k, and that's why we write the k in front. So the kx is the argument of the trig function. Right. If that is the case, then this will probably multiply by the k to it, but it is not. What we actually do is y equal to ln of kx. And we have the function of kx. When we take derivative, is 1 over the parentheses, and then derivative of the parentheses. Derivative of kx is k. So we have k over kx, and the k cancel out. So all of them have the k in front of it, except for the ln, we just have 1 over x. Even there's a constant k, but the k cancel out. Either that, or we can write y equal to ln of kx. We split equal ln of k plus ln of x. And when we take derivative of ln of k, that the constant will be 0. Derivative of ln of x is 1 over x. So it doesn't matter what the constant k is, integral of ln kx is going to be just 1 over x. So everything else we multiply by the k in front of it. Right. Now we'll go to integral. System here. Right. Sine of kx dx. Now, if this when derivative we multiply in the antiderivative or the integral, it will be divided. Integral of sine is going to be cosine. I mean negative cosine. And we divide by k. Integral of cosine kx will be 1 over k sine kx. Right. Tangent kx dx. Right. Tangent, integral of tangent is ln of secant and we divide by 1 over k cotangent be negative 1 cosecant, but this is somewhere in the note to go back. Here. That 1 over k ln of sine kx, and then secant 1 over k ln secant plus tangent kx plus c. Right. Cotangent kx, sorry, secant, this is cosecant is ln and then 1 over k ln cosecant kx minus cotangent kx plus c, and finally e to the kx is e to the kx divided by k. Right, so that's all we have. Let me change the camera a little bit. There's something off. Right. Yeah, zoom out a little bit. Yeah, that better. Right. So that's all we have. On the big scheme of things, the derivative doesn't change much. The only thing that changed in the derivative is we multiply by k, except for the ln, and on the integral we divide by k, and then we don't have the integral for ln of kx yet. Right. Now go back to derivatives. I mean integration by parts. Okay. Now go to the table of method. Right. So the step to evaluate is pretty much here. So I just write the highline. So we use that to find u to differentiate. So we find u and then we take derivative, and the way we do that, we use that acronym. And then integrate the other term. Three. Find the product, meaning that we multiply diagonally. And alternating sign. And if we have to stop, do not vanish. Use the horizontal line. Use the horizontal product and integrate. Right. That doesn't mean much if we don't know what it actually do. Right, so what we do is now we just go to an example, and then we see how do we do it. Example 1. Right. So we integrate this. So the first thing we do is, of course, the mnemonic LIATE, and then we check, go to that list and find out what is u, what to be differentiated. So there's no log, there's no inverse trig, and there's algebraic, which is a polynomial 5x. So that is going to be the term that we differentiate. So this is called the table method. So we have to make a table. Right. So we find something to be differentiated, and the other term will be integrated. Right. That is going to be 5x. It's the term to be differentiated. And so we just take derivative. Derivative of 5x is 5. Derivative of 5 is 0. And derivative of 0 after that is going to be 0. So choose a term to be differentiated, and that's given by this, the priority. So log, inverse trig, algebraic expression, polynomials, and then t, trigonometry, and then exponent. Right. So this is the term to be differentiated. The cosine 2x is the term to be integrated. So integral of, that's why we write this out earlier. So integral of cosine of kx is 1 over k, in this case 2, sine of 2x. And then integral of sine of 2x is negative 1/2. So we have 1/2, the constant there, and the sine derivative, the integral, will be negative 1/2 sine of 2x. Which is negative 1/4 sine of 2x. Right, so one term to be differentiated, the other to be integrated, one derivative, one integral, and after that we form the diagonals. So the northwest and southeast diagonal. So the first one is that we'll have the positive sign, and the second one, by the way, we check the final result. Also the diagonal product, the next one is negative, and then positive, negative, positive, negative, just alternating like that. Right. So, and that's all we do, really. We just write out the result. 5x cosine of 2x dx. Right. The first product, 5x times 1/2 sine of 2x. And then next, minus 5 times minus 1/4 sine of 2x. And then of course we continue with the next one. However, since we have 0, the product, all the products after this is going to be 0. So that's why we only have two of the terms. Everything else will be 0 because 0 is one of the factor plus the constant c. So we have 5x divided by 2 sine of 2x, and minus 5 times minus 1/4 positive 5/4. This should be cosine, sorry. Cosine of 2x. So that's what we have in the note. Right. So one derivative, one integral. Right. Now go back to the note from last time. Right. What I have from the last page, from the note from last time. We evaluate this derivative. Now we use the table. Last time we used iteration by parts and we used the formula. Now this time we just use the table. And that example, of course, are here from last time. Right. So if we use the table method, we will have something to be differentiated, something to be integrated. And u is what to be differentiated. So we have x, and then we take the derivative of x, which is 1, derivative of 1 is 0, and will be 0 after that. Now the integral is what's left, e to the x. Notice that we just write e to the x and we don't write dx in this case when we put the table method. Now we just integrate. Integral of e to the x is e to the x integral of e to the x is e to the x. So we just integrate. It just happened to be the same thing. Integral of e to the kx, 1 over k, e to the kx. Now if k is 1, that's what we have here. Alright, diagonals, positive, negative. So we have integral of x, e to the kx, e to the x. Dx is going to be x times e to the x minus 1 times e to the x plus c, which is x e to the x minus e to the x plus c, which is exactly what we have here. Right? So, same thing here. Make a table. One term to be differentiated. The other term is integrated. Right. So, and we use u to be 2x plus 1. So we have 2x plus 1. Derivative of 2x plus 1 is 2. Derivative of 2 is 0. And will be 0 after that. Integral. We have sine x. Integral of sine x is negative cosine x. Integral of negative cosine is negative sine. Keep adding the k to it. Right? And then after that, sine is it's going to be cosine, and afterward it doesn't really matter here for that term because we multiply by 0. Right. Notice this is not derivative. This is integral. And we just do not provide a constant c, but that those are actual integral. Right. Now, the product, diagonally, positive, negative. So what we have, integral of 2x plus 1 sine of x dx equal to the first product, 2x plus 1 times negative cosine x, subtract, because that's negative, 2 times negative sine x plus c. And so just move the negative in front, negative 2x plus 1, and then cosine of x, and minus, so that's the plus 2 sine x plus c. So that is where we use the table method. We have 2 rows. So we have 2 rows. 1 row for derivative and 1 row for integral. And the derivative choosing from logarithmic function, inverse trig, algebraic expression, trigonometry, and then exponential. And algebraic expression is a polynomial or something similar to it. It's classified as A, so that's what we have here. Right, and just integrate. That's why we review this before we jump into integration by parts. Now, so that's what the note we have from last time. And even before that, when we say right after this, we say we have the note, and then we just leave about 3 lines. Right. So what do we need here is pretty much u is to be differentiated, and we have to do something that we can differentiate. So that's good. However, we have to be able to integrate u v. And sometimes we cannot integrate, and these are the function like this. When we have, I'm just write some example here. Sub x squared or e to the, where we have something like that, we cannot integrate without substitution. We cannot integrate this function without substitution. Now we get back to that. Get back to the note for this next continuous section. So again, we should not have anything like this. Bottom line is, when we see something like this, this is not integration by parts, because we cannot just simply integrate this. What we can integrate, well, is just those with the constant times x. Those are what we can integrate. We can have sign of kx plus another constant, but that's fine. But when we have an x squared here, we have to use substitution. That one's okay, but if we have the power of x in the trig or exponential function, it has to be substitution. So that are some of the questions on the review that you see. Right, 2. Oh. What note? Yeah, you mean that? Yeah, we cannot integrate those terms without substitution. Okay, this one, yeah. Yeah, so we can always differentiate it, but the thing is, sometimes we cannot integrate. So we choose something that we can integrate, and those things are the term that we cannot integrate. Right. So bottom line is usually will be this term, that to be the term to be integrated will be on this table. Right. Evaluate this integral 2x squared plus 4 e to the negative 3x dx. Why for some reason I write k? Right. So make a table. One column is derivatives, the other column is integrals. So from now on we only use the table method. I'm not going to go back and use, we use the formula, which is perfectly fine, but the table is more compact. Right. So in the table, what we just need to choose is choose the term to be differentiated, LIATE. In this case, what we have is a polynomial here, which is a, because there's no log, no inverse trig, there's a polynomial which is a exponential, is last on the list. Right, so we have 3x squared plus 4, and we just keep taking derivative. Derivative of 3x squared plus 4, 6x. Derivative of 6x, 6. Derivative of 6, 0. Yeah, just keep taking derivative successively. So if that is u, and the term to be integrated is going to be e to the negative 3x. So there we have e to the negative 3x. Right, so what's that integral? This is from the first page of today's note. Right, integral of e to the kx is 1 over k e to the kx. K in this case is negative 3. So we have 1 over negative 3 e to the negative 3x. Don't need to have the constant. Don't write a constant. So which is negative 1 over 3 e to the negative 3x. Right. And then integrate one more time. That constant will stay there. Integral of e to the negative 3x is going to be the same thing. 1 over k, and then e to the kx. Multiply them out, we have 1 over 9 e to the negative 3x. And then integrate one more times, 1 over 9. And integral of e to negative 3x, we did this already. 1 over negative 3 e to negative 3x. So that is negative 1 over 27 e to the negative 3x. Right? So we just keep integrate. Integrate something kx, we divide by k. And so that's what we have, 1 divided by negative 3 and 1 divided by negative 3 on all of them. Right. Now focus on the last one. Right, the diagonals. First one positive, second one negative, next one is positive. Right, so now we just write out the result. So first up, the product, 3x squared plus 4, and then we have negative 1 over 3 e to the negative 3x. Next is subtract 6x times 1 over 9 e to negative 3x. And then next is the plus 6 times negative 1 over 27 e to the negative 3x. And the next one could be 0. So that's what we have. Right. So we multiply them out. I will take the constant in front. Negative 1 over 3 e to the negative 3x. And then 3x squared plus 4. And then 6 divided by 9. 2 over 3. And 6 and 27. 2 over 9. So if we have to use iteration by parts on this problem, we have to use iteration by part twice. But when we put in a table, it doesn't matter. We just systematically write out a column of derivative, a column of integral, and then we just do the diagonals, alternating signs. Right. The next one is kind of classic problem. You certainly will see one of this on the test. Oh, sorry, that was the first one. 2. e to the 3x sine of 5x dx. Right. Like I said, one of these problems should be on the test. But by this type of problem, what I mean is we have an exponential times a trig function. So it could be e something and then sine or cosine. Yeah, but that's what we have. Right. Now, of course, make a table. Something to be differentiated successively. The other one will be integrated. Right. Now, what do we choose? L, I, A, T, E. Right. There's no log, no inverse trig, no algebraic expression. So there's only the trigonometric function here. So that the term we choose to be differentiated is the trig function. So sine of 5x So on this one, slightly make bigger table. Now derivative. Notice that this time is derivative. When we take derivative, we multiply by the constant k. When we integrate, we divide by the constant k. Right. So derivative of sine is cosine, and then we multiply by the constant k. So it's going to be 5 cosine of 5x. Just put parentheses around 5x. Right. And then derivative of cosine is negative sine. And then multiply by the constant k. That should be sine. Right, derivative of cosine 5x is negative 5 sine of 5x, and that gives us negative 25 sine of 5x. And then derivative again is going to be negative 25. And derivative of sine of 5x is 5 cosine of 5x. 5 times 25 is negative 125 cosine of 5x. Right. I think that's more than we need. And then we can check derivative. But when we do that, it will not go to 0. Just say, do not vanish. So that does not go to 0 when we take derivative of that. Right, so it's fine. We're still okay. Right, now integrate is e to the 3x. So derivative is where we divide, derivative is where we multiply by the constant k, and integrate is where we divide. So we have 1 over 3 e to the 3x, and then e to 3x is 1 over 3 e to the 3x, which is 1 over 9 e to the 3x, and then we keep integrate 1 over 9 and then divide by 3 again. 1 over 27 e to the 3x. And then of course we can just keep doing that, but we're not doing it. Right, now, so, and that is what we have. Now, let's just start writing out the terms. So, sine, cosine. Right, it's going to be a long problem, so I start all the way here. Right, first, the product. Positive. We have sine of 5x. And 1/3 e to the 3x. Right? First product. Next. Subtract. Five cosine 5x. 1 over 9 e to the 3x. right? And then next, we should write the diagonal, but we cannot just do that forever, because that do not vanish. None of them will go to 0. The last two problems we can do that, because if the table go to 0, all the diagonals after that is going to be 0. So in this case, we cannot do that. We have to stop. And when we stop, in this case, we stop after the 2 steps. So that is the classic part of the problem, where we have an exponential and a trig function. We do that two step, and then we stop. Right. So when we stop, we do not do the diagonal. What we do is we do, write this in red. It is going to be the horizontal. And we use the integral. So that line stop. And the signs still alternate positive, negative, and positive. So we will have an integral of negative 25 sine of 5x, and then 1 over 9 e to the 3x dx. So that is the difference. When we stop, the plus sign actually, when we stop, we use the horizontal, but with the integral. And of course the integral goes with dx, so that's what we have. Right. Let's simplify this a little bit. Maybe we have something. 1 over 3 sine of 5x e to the 3x minus 5 over 9 cosine of 5x e to the 3x, and that gives us negative 25 over 9. Take the constant outside. Be negative 25 over 9, and then the integral sine of 5x e to the 3x dx. Right. So we do this 2 times, and then we stop. When we stop, there's an integral. And then the question is, why do we stop after 2 steps? Okay, here's why. On the big scheme of things, when we look at this sine, cosine, we get back to sine, right? Now, if you look at this problem, original problem, and this one, is that the same as this term? Yeah, I just write them backward, right? But they exactly the same thing. So let's rewrite that. Let that integral be an integral I Right. So that's the beauty of it, or the trick of it. Now what we do is we solve for I. So we're going to add 25 over 9 I on both sides. So 1 plus 25 over 9 fraction 34 over 9. Of the integral I times 1/3 sine of 5x e to the 3x minus 5 over 9 cosine of 5x e to the 3x. And now to solve for I, multiply both sides by the reciprocal. So the integral I will be equal to reciprocal on the other side, meaning 9 over 34 times 1/3 sine of 5x e to the 3x minus 5 over 9 cosine of 5x e to the 3x, and then plus a constant c. Right. So that's what we have. Of course, we can always multiply this inside, and finally we have the integral e to the 3x sine of 5x dx equal to, multiply this out, 9 and 3 cancel out, 3 over 34 sine of 5x e to the 3x, 9 and 9 cancel out, 5 over 34 cosine of 5x e to the 3x plus c. Right. So that's how we integrate. Oh, we have 1i on this side and 25 over negative, not 25 over 9 on the other side. So what we do is we're going to add 25 over 9 times I on both sides. 1 plus 25 over 9 is 34 over 9. That's on the calculator. Yeah. So we're going to move this to the other side, and we add 25 over 9, and 1 and 25 over 9 is 34 over 9. Multiply reciprocal, 34 over 9 becomes 9 over 34. Right. So, like I said, you should have one kind of problem like this on the test, where we have a trig function times an exponential, and then of course I recommend using the table. Right. So we will do this a few more times, where what we call is find the integral indirectly. So we did not do this from the beginning. I mean, we still don't know how to integrate that directly. What we have to do is just integrate and just happen to have something that have the same terms I. So move them on one side and we solve for it indirectly. So that is a classic problem, and pretty much every time I teach anything that involves integration by parts, we have to have this kind of problem. So a few things to note here. Note, we use integration by parts, and it will be the same terms after 2 steps. For this kind of problem, so use integration by parts twice, meaning that after 2 diagonal, it will get back to the same thing. After we do this twice, we should get back to the original integral. And then solve for that integral indirectly. By this we mean we solve for that indirectly. We don't know what iron is, but in this equation it will work that we can solve for it. So those are the steps. Yes, but like I said, well, you get used to it when we have the derivative and then integral. There's only one problem. I mean, maybe more than one in the homework and one problem on the review. Yeah, but definitely you see this kind of problem on the test. Right. Right. And notice that we do it integrate twice. For the type of the problem, I mean 2 diagonals and then the horizontal line. For the problem that we have an exponential to the kx and then sine another, let's say ax, or we might have an exponential with the cosine. Either way, so this is very good exercise about derivative and in integral, and then we do that. Like I said, after a few problems, you get kind of the pattern. By the way, here's a trick to that. Also, you should have something when we divide by, we have a 34, right? So where that 34 come from? If you think about that, the 34 is equal to is that equal to 3 square plus 5 square? Right? And where's the 3 and the 5? The 3 and the 5, right? So you should have the 34, which is 3 square plus 4 square when we divide on both sides. That's where the 34 comes from. And the 9, because it's the 3 square. Yeah. So, and where's the 9 coming from? It's going to be the 3 square. So, in general, for this type of problem, at the end we will have the integral equal to, I'm not sure the rest of the problem, but what I can say is we're going to multiply by the integral of k squared divided by k squared plus a squared. If you do that correctly, we should have that multiplied by something plus c. Right. Ouch. Sorry. Should hit the camera like that. Right. So on the review problem, by the way, I posted the review online just last night. I did that on Friday actually. I mean, yeah, on Friday. Right. Remember, we have e to the kx and e to the kx and then sine cosine. At the end, we should have k squared over k squared plus a squared. Right. Now, what we have in this problem, we have. By the way, this is on, like I said, is online already. What we have is -4 and then 8. Those are the coefficients. So at the end, I said we should have, at the end, we have -4 squared over negative 4 square plus a square. Right. So, yeah. Exponential k, I mean the coefficient of exponential square divided by that square plus the coefficient cosine cosine. And that gives us 16 and 64, so that 80 would reduce to 1/5, right? And of course we should have 1/5 if that helps at all. So when we do this twice, we should end up with the k square over k square plus a square. Right. I'll take 5-minute break here. We continue at 9:15. Before we continue, notice that this kind of problem, when we integrate twice, and to get back to the original integral, we do that when we have the exponential and the trig together. So not every problem we do that twice. And sometimes like the secant cube, we see that later. Right. E. Right. So this is we did not do in calculus 1. Remember when we go to the integral of ln of x dx, this is what we need the integration by parts in calculus 2. This is what we're going to use. Right. ln of x dx. We'll try to do that. Right. Now let's choose something to be differentiated, something to be integrated. Usually there's ln. I should not say that. So when we have the ln, we might try the integration by parts, unless there's something different. We'll go to that in a minute. Right. So what do we choose? L-I-A-T-E. All right. We see the log. So that is the first one. Right. The derivative of ln of x is 1 over x, right? Or we write x to negative 1. And then the derivative of that is negative of x to negative 2. And then so on. It's not going to go to 0. Right? And then in that case, what do we integrate? There's nothing left, right? I just have the dx. So in that case, what we integrate is going to be 1. Integral of 1, integrate of 1 is going to be x. Integrate of x, x squared over 2. And then so on. Right? So because this integral dx is just x, and integral of x is x squared over 2. So just like that, integrate and differentiate. Just like that, right? So ln of x dx equal to, let's just write out the first diagonal positive, ln of x times x. The next one is negative. But we cannot just keep doing that, right? If we keep doing that, we just do the diagonal non-stop. So instead of doing that, instead of do the whole bunch of diagonal, I just stop here on the second step and use the integral. We have x to negative 1 and then x So instead of doing a bunch of diagonals and we don't know where to stop, so let's just stop after the first step. Well, the last problem, the reason we stop after 2 steps, because so we need to get back to the original integral. That's why we need to do that 2 steps. On this one, we stop right after the first diagonal, and then we stop instead of doing a bunch of diagonals, right? So which give us x times ln of x minus the integral x to negative 1 times x to the first. So we just add the exponent x to negative 1 plus 1, so just 1. So what we have is x ln of x minus integral of 1 is x plus c. So what we have is integral of ln of x dx so that is the integral of x ln of x, ln of x dx. Now, and you probably wonder what happened if we do a few more diagonals. It will work, and the answer to that is it will work just fine, right? Now, by the way, that is the answer. What I do here is that, let's say we have do 2 diagonals. Right, the first one is still ln of x times x. The next diagonal will be minus x to negative 1 times x squared over 2. And then we decide that we stop at this step. Let's say if we stop at the second step instead, x negative x to negative 2, and then x squared over 2. Right, this is where we stop after we do 2 integrals. That gives us x ln of x, and this is negative 1/2 x to negative 1 times x squared. Add the exponent, we have negative 1/2 x negative 1/2 integral. Multiply this together, add the exponent, just have 1. So we have x ln of x minus 1/2 x. Integral of 1 is also 1/2 x. And a half and a half is a minus 1. Yeah. So bottom line is whether we do 1 diagonal and then stop, or we do 2 diagonal then stop, or we can do a bunch of diagonals and then whenever we stop, we should get the same thing. So that's why we don't need to do that 2 steps. We just do it once and it's good enough. Right? So remember, every time we have the ln, right, have to be careful. Sometimes we use iteration by part, sometimes we don't. Right. I just give you a sample here. So we have this problem. Those are the problems that I think of. The problem where we have ln of x in it. Right? Now, actually, on these 3 problems, only one of them we have to use iteration by parts, the rest substitution. Right. On this one is the one where we use iteration by parts. The other substitution. Right. And ask you what is the difference of those 2 types of problem. Right. So the difference here is this one we have just ln of x multiplied to it. Right. This we divide by ln of x. This ln of x at the bottom. And this ln of x has the power. 1 under denominator, 1 has the power. So when we now have something other than just multiply by ln of x, that we use substitution. Iteration by parts, where we have ln of x, it is where we multiply by just ln of x. If we have something else, that's not iteration by parts. Right. Yeah. Oh, keep this in mind. On the test review, there's a question like this. So iteration by parts for definite integrals. Let me write this out. Now we have the integrals, but with the limit. Still u dv, so it's going to be u v integral from a to b and minus v du. Right, so it's not big of a deal. It's this type of problem. Instead of having a constant c at the end, we just have that integral and then evaluate. Right, to width. Let's go to the next example. I should write this in blue. So we evaluate integral from 1 to 2 ln of x dx. Right. Right. So, of course, we do the same thing. Actually, I mean exactly the same thing because we did the ln of x, right? Integral ln of x is going to be this. So, all I say here is see previous example. What we have is equal to x ln of x minus x. But instead of plus c, what we do, we just evaluate from 1 to 2. So that's the difference between definite and indefinite integral. Instead of a constant c, we have the limits. Right. Put 2 in for ln of x. In for x, I mean. 2 ln of 2 minus 2 minus 1 ln of 1 minus 1. So 2 ln of 2 minus 2, ln of 1 is 0, right? And then minus the negative, it's going to be plus 1. So we have 2 ln of 2 plus 1. Right, so we just integrate like we normally do in the integration by parts, and then instead of a constant c, we have the limits, and then evaluate. So not much difference. Evaluate. Right. So even with the limits, we just integrate and integration by parts like we normally do, meaning we're going to use the table. Right. So what do we choose to be u to be differentiated? So differentiated usually is the term we call u, so which is LIATE. There's no log, no inverse trig. And then we have a polynomial, which is an algebraic expression. So that's what we have. 3x minus 1. So that's what we choose to be u. That's what we choose to be differentiated. So 3x minus 1, derivative 3, derivative of 3, 0, and afterward integral e to the x. Now that's easy. Integral of e to the x is e to the x, then e to the x, and then pretty much the same thing. After that doesn't matter because the diagonal would be 0. So this one vanishes to 0. Right. So integral of 0 to 3, 3x minus 1 e to the x dx equal to first diagonal positive 3x minus 1 e to the x, next diagonal minus 3 e to the x, and everything after that is going to be 0. So that's all we have, really. But this time with the limit, so what we have to do is, instead of a plus a constant c, we will evaluate from 0 to 3. Right. Before we do that, it could be nice if we factor out e to the 3x here. I mean e to the x. Let's factor it out. Factor that we have 3x minus 1 and then minus 3. Right? Factor out e to the x, we have 3x minus 1 minus 3. So which is e to the 3x minus 4 going from 0 to 3. Now just put 3 in for x. E to the 3 times 3 times 3. I don't know why I have e to the 3x here. It's just e to the x, right? E to the x. Put 3 in, so e to the third power. Three times 3 minus 4. That's where we put 3 in it. And now we put 0 in it. So that is e to 0 power is 1. 3 times 0 is 0. So we have e cubed. 9 minus 4, so it's 5. Minus, I just write out 1 times minus 4. So will give us 5e cubed. Yeah, sorry, that come out nowhere. It's just e to the x, and I just copied it wrong. Minus the negative, so that's a plus 4. Right, so that's what we have. Sorry about that. Let's check and see if it works. Notice that the definite integral, we kind of indirectly check the answer. Right? And maybe this is the same 5 times e cubed plus 4. Yeah, so that's good. Right, so we just integrate integration by parts like we normally do, but this time we have the limits. So we're just going to add and evaluate it. Right. Evaluate. Okay, so now we have this form. So now, of course, the title says, is this integration by parts, or is that a substitution, or how do we know? Right. So let me ask you this. Compare this problem and that problem. What is the difference? The difference is not the polynomial. They both polynomial. The difference is e to the x cubed. Do you remember we have that one, right? If it is multiplied by something, it's good. Other than that, substitution. That for the LN though. Remember we write this note earlier, right? The note where say 3 lines. So that's why we put something there. Right. So if we have sign of x squared or x cubed or anything else other than the kx. If we have e to something else other than x, other than kx, that is not integration by parts. That is substitution. Bottom line is, if we have this kind of function, we can integrate. That just have kx. If we have more than that, x squared, x cubed, something like that, it is going to be substitution for sure. Because of that, what we have here is the x cubed on the exponent. So this has to be substitution. If this is just x, now for example, if instead of this problem, what we actually have, if we have e to the 3x, then this one is integration by parts. The difference here is just on the exponent. If it is x cubed, this is going to be substitution. So this one is substitution because of x cubed. If it is 3x, perfectly fine. 5x, e to the 5x, perfectly fine. E to the x squared, e to x cubed, any higher power of x, that is substitution. Right, substitution. We let u equal to x cubed. Yeah, kind of have the x squared to cancel out as well. So, right? So we check derivative. Now this is just substitution. 3x squared multiply dx and then divide by the 3x squared. So we have 5x squared e to the u dx is this. X squared cancel out. 5 on top. 3 at the bottom. So 5 over 3. Integral of e to the u is just e to the u plus c. And u is x cubed. Right. So this is just substitution and not integration by parts. Right. B. Integral of ln of x over x dx. You on the note, there's a line, which means we only need to do it on the half of the page. So my question is this going to be iteration by parts, or is that going to be substitution? By the way, if it is iteration by parts, it should be written as a product. So let's write this as a product. X at the bottom, if we move to the top, it becomes x to the -1. Now we have the product. Right, so let's use iteration by parts. Right, so of course, iteration by parts, there's a log. Derivative of ln of x, 1 over x, or we can say it x to -1. And then we just can keep taking derivative, negative x to -2, and then so on. Right, so that is u to be differentiated. And what else is going to be x to -1, that to be integrated. Right, so integral 1 over x, what's that? Now we see derivative of ln of x is 1 over x, so antiderivative 1 over x is ln of x. And then here we have integrate ln of x is x ln x minus x, so we don't even know what it is. So in this problem, what we have is the first one, and then we stop. Right, so I will write this out. We start with this ln of x, x to -1 dx equal to ln of x times ln of x, ln of x times ln of x minus the integral x to -1 times ln of x dx. We cannot go any further because we cannot do integral ln of x without iteration by parts. Right, so what do we see here? Now, this trick we've seen before. By this trick, I mean this is an integral I, so is that. ln of x times ln of x is ln of x squared. So we have I on this side and negative I on the other side, so we move them to one side. 1i plus another I is 2i equal to ln of x squared, and then divide by 2. So the integral is equal to 1/2 ln of x squared plus constant c. Right, as mentioned before, we see this trick before when we have the I and then end up with also the same thing. So in that case, move everything on one side and solve for it. We call that indirect iteration by parts. Right. Now, the reason we draw a line here and only do half a page, because the other half we can use substitution. So our problem is ln of x over x dx. Right, the substitution. Let u be ln of x. And then we'll take the derivative of ln of x. Which is 1 over x. Cross multiply x du equal to dx. Yeah, just cross multiply. And that gives us dx. So I have ln of x, which is u, over x, and dx is x du. X and x cancel out. We have integral of u du, which is u squared over 2 plus c, and u squared, u is ln of x, and we have the same thing. Right, this one and this one. So on this problem, we use both integration by parts or substitution. Both of them works. But usually the rule of thumb, unless we have ln of x times something directly like this, that integration by parts. Other than that, I prefer to use substitution. So only use integration by parts where we cannot use substitution. And we have a little note here. You mean the I? Oh, usually when we do the integration, and if we end up with the same thing as the original problem, then we call that the integral I. That's not number 1 or I or anything. I call that I this for the integral. And we just solve for it indirectly. Right. So note. First part of the note here is we cannot integrate. By we, I mean everybody. No, nobody can integrate this. We cannot integrate these functions. Using what we know. And this function will be on the list. This list So we cannot do that. But nobody can do it. Could be x cubed or as well. I should do this. Sine x over x, so so this is, like I said, we cannot use the known function to evaluate. So that's why if we look it up, it is actually an error function. They define this as an error function, and then define this too. I think it's spelled first. Probably. Yeah. So that is something that we don't have the answer. So we just define that as the new function. Right. When we have this kind of problem, we have to use substitution. And then the next one, I want to write the deal with the ln of x. It is integration by parts. If we have the integral of ln of x times something, unless we have, if we have divided by ln of x or ln of x raised to another power, that will be substitution. We use substitution if we have something like ln of x raised to some power or we have something divided by ln of x. Yeah. So those are the little notes. Right. We will not do the next one, but I just want to ask you this. Let's say we have this problem. 2x cubed sine of x squared. So on this one, do we use integration by parts or substitution? Right. So what we do here is, since we saw the sine of x squared, this one cannot be integrated. So this one we use substitution, u equal to x squared, and then we continue. So actually on this one we use substitution first, and after that there will be integration by parts. So let's see. Right. I'll let u equal to x squared. Then take derivative. Move the dx. And then divide by 2x. So we have 2x cubed sine of u dx is du over 2x. We cancel an x, and x cubed cancel here. That gives us x squared left. And then the 2 over the 2 also cancel out. So I end up with x squared sine u du. Luckily, x squared is also u. And then we use integration by parts after that. So this problem we have to use both, but have to be substitution first for sure, because we cannot integrate this. No one can. Right, last problem in this section. Right. Right. How do we do this one? Right. Is that substitution or integration by parts? By the way, if it is integration by parts, it should be a product. So what I will do is, why don't we move the a to the 3x from the bottom to the top, and just change the sign of the exponent. So I have x squared e to the negative 3x dx, and this one definitely integration by parts. Because of a to negative 3x, certainly something we can do. So that's why we write this at the beginning of the class. If we have a to the kx, that's certainly something we can integrate. Right? So in that case, integration by parts, and then just differentiate and integrate x squared to x 2 and then 0, and then do the rest. Right, so I'm not even finished this problem, but that's what we do. Right, I take a 5-minute break. When we come back at 10:10, we go to the next section. Also, before section 8.3, write out all the information, all the formulas that we need for this section, kind of like the iteration by parts. Trigonometric integral. By the way, the next section is trigonometric substitution. So might be a little bit confusing. That's why I cut off it right here and make the first test up to this section and the later part before the next test. Right. Let's review. So, basic trigonometric integral. So sin x dx equal to negative cosine x plus c integral cosine x is just sin x secant square give us tangent and cosecant square negative cotangent and secant tangent give us secant cosecant cotangent negative cosecant. Those are the basic. What we also have that I forgot to put on the notes is the integral of tangent, cotangent, secant, and cosecant. So I'm going to write that here too. Integral of tangent is ln of secant x plus just secant x. Right, cotangent x is ln of sin x secant x. So that one is the secant plus tangent. And cosecant x ln cosecant minus cotangent so those are the basic integrals. Next, the power reducing. So I just write trig identities. With including the power reducing. So we have a square. So reducing the power from square to 1, and then cosine. So reduce the power from square to 1, and then the double the angle. This comes from the double angle identity, where we have a sin x, cosine x. This is going to be 1/2 sine of 2x. Or from here we can say this is also from product to sum. Product to sum identity. And then next, Pythagorean identities. Cosine square plus sine square is 1. Tangent square plus 1 equals secant square, and cotangent square plus 1 cosecant square. Right. So those are all the things, all the formulas we need to be able to do the problems in this section. Right. So that's why I write this on a separate page. So we can reference that. Right. 2. Integral involving power of sine and cosine. Right. So the first part of the section where we have the power of sine and cosine. First, if the power is odd, so instead of writing like what we have in the note, I will write differently. So let's say if we have the integral of sine and cosine, if the power of sine is odd, if we have sine raised to an odd power, and then cosine could raise to any power. So I just put a k and a constant there. It doesn't matter if the power is odd on the sine. Then what we do is let u equal to cosine of x. Likewise, if we have the power of cosine is odd, and then something on the sine, we will let u equal to the other one. So whatever has the odd power, we let u equal to the other function. Now if both of them are even, power, we cannot use this. We can only use power reducing. Meaning that we're going to use this too. Let's look at some examples. So we'll do that one first. Right. Now, by the way, it should not be any problem, but when we write like that, we mean we have the sine x square and then the cosine of x cubed. That's the same thing, right? Now, so what do we use? Let's go back to the rules here. It says whenever we have a sine or cosine raised to an odd power, we're going to let u equal to the other function. So the other function, we have the odd here. Which means we're going to let u equal to sine x, the other function. Right. Now if u is equal to sine x, take derivative. Equal cosine of x multiply the dx. And divide by cosine of x. Right. So I have the substitution. Let me rewrite this again from here. Sine square is going to be u. And then we still have cosine of x cubed. dx du over cosine. And then the cosine of x cancel with one of the cosine. There's 3 of them, so we have 2 left. So that's good, but we still have cosine of x though. By the way, the power here we can always write like that. Right? And now, what do we use? We have u is equal to sin x, so somehow we can go back to that. It would be nice, and there's certainly a way to do that. We have cosine square plus sine square equal to 1. So to solve for sine square, we subtract the cosine square. Cosine square equal to 1 minus sine square. And we use this for the cosine square here. One minus sine square instead. And that turned out to be very nice because that way will let u equal to sin x. So that part here is u squared. So just have integral of u square 1 minus u square du. And then multiply it out. U square minus u to the 4th du. And integral will be u cubed over 3 minus u 5th over 5 plus c. And finally u is sin x, so I have sine cubed and minus sine to the 5th plus c. Right. So the rules here is whatever sine cosine, if one of them is odd, we're going to let u equal to the other function. And then we use substitution. We use substitution for that. Right, next. Right. What will happen in this problem? That's an even. That's even. So we cannot use those two. Have to use the power reducing. Right. One way to do it like that, or we can use just use power reducing then, because both of them are even. So we have to use power reducing. So sine square is 1 minus cosine of 2x over 2. And cosine square 1 plus so that is power reducing. Right, I multiply the top with the top, the bottom with the bottom. The bottom is easy. 2 times 2 is 4. Right, the top. 1 times 1, 1. 1 times cosine of 2x minus cosine of 2x minus cosine times cosine. Give us cosine square of 2x. Luckily, those cancel out. So when both of them are even, we have to use power reducing formula. And we split this, we have 1/4 minus cosine square dx. Now, we have the integral of 1 over 4. We split, which is just 1/4 x. And then the other one we will have the integral of cosine square. And that's 1/4. Don't forget that. So integral 1/4 is 1/4. Stick an x to it, and then this one is still even power, so it's still power reducing. So still have to use power reducing for that. So the power reducing meaning that reduce the power from 2 to 1, and the angle will be double. So we have 1/4 x and minus 1/4 integral. I will split this in 2. And split this into integral. The 2 stay at the bottom, break it outside, become 1/2. And then we'll just integrate 1/4 x minus 1/4. 1/2 integral is 1/2 x plus 1/2 cosine 4x integral is sine of 4x. I can do that because that is the beginning of this section where we have cosine of kx. So 1 over k sine of kx. So that. And finally, multiply it all out. One fourth x minus 1/2 times 1/4 1/8 x minus this and minus 1 over 4 times 4, 16 and 2, 16 times 2, 32. One-fourth minus 1/8. One-eighth is 1/8. And that's what we have. Right. Next. Next we have this one. Right. So I will rewrite this as sine x cubed cosine of x to -2. Right. Now, on this one, what we have is the power is odd here. So which means we use substitution. Let u equal to the order function cosine of x. So every time we have an odd power on a sine, let u equal to cosine. And if we have an odd power on the cosine, let u equal to sine. Right. So we take derivative. Derivative of cosine is negative sine. Move the dx over. Divide by the negative sine. Right. So we use that substitution. I go back to this problem. Right, now use substitution. The sine cube is still there. The cosine, which is u now. And dx, du over negative sine x. Sine x cancel with sine x. There are two lefts. There's a negative sign. Move to the outside. And then we have sine x squared u to negative 2 and just du. Which let me rewrite as negative sine squared right. So it's good if somehow we can write this sine squared in terms of u. Then it will be very good. So every time we have a square, try utilize Pythagorean identity. So we solve for sine square. One minus cosine square, and we substitute that in here. And the nice thing about this is cosine square here. U is cosine, so cosine square is u square. So we have negative 1 minus u square u to negative 2 du. Multiply it out u to negative 2 and then multiply these two. Add the power 2 minus 2 is 0. Which is 1. So we have negative u to negative 2 minus 1 du. So the integral u to the negative 1 divided by negative 1. Integral of 1 is u plus c. And finally, distribute the minus. Negative and negative cancel out. Negative, negative. And finally, u is cosine of x. Right, so that's what we have. So pretty much, just substitution. If the power is odd on the side, u equal to cosine. If the power is odd on the side, then u equal to cosine. Just use the opposite. Not opposite, I mean the other function. And then when we do that, try to write everything in terms of u. Most of the time we need to do this identity. Now we have sine to the fourth power. Right, so let's check. Do we have any odd power? That would be none. So because of all of them are even, which means we have to use power reducing. But even then, it's not all of it. So how does? So the sine to the fourth, we will write as sine x to the fourth power. And then the fourth power is the square and then square. And then the power reducing, the sine square is going to be 1 minus cosine double the angle divided by 2. Right. The power reducing, sine square is 1 minus and then we square, and then when we square we still have a square, so still power reducing after that. Right, 1 times 1 is 1 minus cosine 2x minus cosine 2x. Minus a negative, that's a plus. 2 times 2 at the bottom is 4. So one, there are 2 of them here. And the cosine square of 2x. Right. And from here we can split the integral. 1 over 4, 2 over 4, and 1. Let me write that again. 1 over 4, 2 over 4, and 1 over 4. And here we still have cosine square. Which is power reducing again. That is 1/2. Forgot the dx. Right. So power reducing, the power reduced to 1, but the angle is going to be double. And then split. I'm not going to finish this problem, but that's what we do. Power reducing. Every time we reduce the power, the angle is double. Sine or cosine. So we go from the fourth to a square. And from the square to the first power. And every time we do that, the angle is double. Five. Cosine of fifth, and then sine cube. Right, so let's rewrite this as cosine of x to the fifth, and then sine of x cube. Right. So now this one is easy. Both of them is odd, so we can use either one of them. We can use u to be cosine of x, or can u to be sine of x, because the other power is odd. So both of them is odd. So both of the powers are odd. We can just use cosine or sine. Right, so I will let u equal to, let's go with cosine. So take the derivative and then solve for it. Solve for du and then solve for dx. Right? Right, I'll go back to this. Right. U equal to cosine of x, so that is going to be u to the fifth. Sine of x, we just have to write like that for now. And dx is du over negative sine. Sine x cancel with one of them, left with 2. The negative sine move on the outside. And that's what we left with. And then when we have the sine square, cosine square plus sine square. So the sine square equal to 1 minus cosine square. So we end up with negative u to the fifth sine square 1 minus cosine square. And then the cosine square, I don't know why I write u, but this will be x. Cosine square is u, so we end up with negative u to the fifth 1 minus u square du, which is simple enough. Multiply it out. U to the fifth minus u to the seventh. And so we have integral will be u to the 6 over 6, u to the 8 over 8 plus c. And then we just substitute back cosine of x, and that's what we have. Right. So since both powers are out, we can use either one of them. I just happen to use u equal to cosine of x. If you want to, you can let u equal to sine of x. So that is the integral when we have sine and cosine. Next, when we have the integrals that involve tangent and secant. Right. But we have to do that on Wednesday because we run out of time. Anyway, so what do we do on Wednesday? On Wednesday, we'll finish this section. Probably will take an hour. And then with that, we finish everything for the first test. So I will post the test by Wednesday. So test 1 will be posted on Wednesday. So here's a few things. So test 1 is posted this Wednesday. Will be the 15th. And then I got asked this too many times. But remember, you have until the end of the semester to do the test. And when I posted the test, it will be on my MATLAB. So test 1 will be posted on my MATLAB. And the due date at the end of the semester. Right. So I will post. It's posted. Test 1 will be posted on Wednesday the 15th on my MATLAB. Tests are due at the end of the semester. And it goes without saying, the test, you just take it on my MATLAB. It will be open book, open note. Because it's difficult to do it otherwise. Right, what else? Oh, by the way, I will post a sample test. This sample test only 4 questions. Uh, 10 minutes. Of course, it doesn't count at all. You just go there and see what is the test will look like, and how do you answer the question, and what the test will look like. Pretty much, this has no values at all. I just want to get experience of the test. The actual test though, on the test, we have 2 hours each. There's a time limit. And there will be 2 attempts. Right. So I highly recommend that you go to the sample test and see how it works on the sample test. On the sample test, you have 4 attempts. I mean, the difference between the test and the homework is that on the test, when you type the answer and you hit submit the answer, I mean, don't submit the whole test. When you type the answer and hit enter to go to the next question, it will not tell you if it is right or wrong. So we have to do that for all the question and hit submit at the end. When you submit all of the question, in that case, it will tell you which one is right, which one is wrong. It will not tell you which the right or wrong when you enter it like the homework. It only tell you when you hit submit and they'll give you the grade for the whole thing. And that is one attempt. And then if you want to, there's another attempt of the similar test. Just do the same thing. Right. So if you have any question, just send me an email. But other than that, that's what we have for the test. And I'm going to post out the next set of notes on the folder. Yeah. I have the note for the next part already. I just didn't post it out. The next test will be from 8.4 to 10.4. But yeah, I'll post the note on the Google Drive. Right, I'll do that. Anyway, so that's what we have. Right, if you have any question, please send me an email. Other than that, I think we stop here. We should finish this section by Wednesday. Probably take an hour. And after that, I will have the test online, and you will take the test online at your own time. We will not spend any class time to do any tests except for the final, which, yeah, we'll talk about the final later. Have a nice day. Thank you for watching, and thank you for